Hello. The following presentation is outlining the project for Capstone Group 5 from Grand Valley State University's engineering class of 2023. This senior capstone project is sponsored by E3 Compliance, an electromagnetic compatibility, or EMC, testing facility which is located inside GVSU's own Innovation and Design Center in downtown Grand Rapids. E3 Compliance completes a range of tests on electrical equipment, one of the more popular being radiated emissions, otherwise referred to as RE, where the electromagnetic noise being radiated from a product is measured from the product to ensure there are no emissions significant enough to disrupt or interfere with communication between electronic devices, including wireless communication. The goal of this project was to create a new antenna mast for E3 Compliance's new 3-meter radiated emissions chamber. The students in Capstone Group 5 include Zachary Davis, Nicholas Hare, Megan Healy, Gidi Muthiani, and Joshua Prybisky. This group consists of 2 electrical engineers, 2 mechanical engineers, and 1 double major who studies both electrical and computer engineering. The faculty advisor for this group is Dr. Ryan Krause. The requirements for this project are to produce an automated antenna mast that is compatible with 4 different types of electromagnetic compatibility antennas housed at the E3 Compliance Test Lab. The antennas currently in use include the following. The biconical antenna, which is able to measure frequencies from 30 to 330 MHz. The log periodic antenna, which is able to measure frequencies from 300 MHz to 7 GHz. The horn antenna, which is able to measure frequencies from 1 to 6.5 GHz. Lastly, a double-ridged guide antenna will soon be added to E3 Compliance's repertoire, which will be used to emit electrical noise from 170 MHz to 40 GHz to test the immunity of a product. It is important to note that the double-ridge guide antenna weighs approximately 26 pounds, which is the heaviest antenna in use, meaning all verification done must satisfy the weight of this load being held at the end of the mast arm. The antenna mast supports manual adjustment of both the height and bore sight angle of the measurement antenna, and supports the automatic rotation of an EMC antenna with respect to the ground plane from outside the EMC chamber. An EMC antenna is a specialized type of antenna used to measure electromagnetic fields and radiation from electronic devices or systems. It is used for testing the electromagnetic compatibility of electronic devices, which refers to the ability of the device to operate without causing interference to other devices or being interfered with by other devices. The antenna mast is a combination of a base, stand, and arm, which holds the antenna in the position desired by the EMC test technician. The design contains very little metal so as not to introduce or reflect significant electromagnetic noise off the device under test, which may interfere with the test measurements. The importance of minimizing conductive materials in the design is to mitigate the risks associated with electromagnetic reflections in the test chamber. The main issue which can occur from electromagnetic reflections in a pre-compliance radiated emissions chamber is the electromagnetic noise corruption of the signal being received. Radiated emissions testing requires an atmosphere which is completely shielded from any noise outside the chamber, as well as minimized opportunities for reflection of noise generated inside the chamber by the device under test. The electromagnetic noise, or reflections of such, can be constructive or destructive to the actual signal of the device under test, which can provide an inaccurate measurement and cause a test to falsely pass or fail. This sort of mistake at a pre-compliance lab could mean that a product goes onto a certified compliance lab, and the results may be different. This can cost hundreds of thousands of dollars, wasted resources, and wasted time. There are 3 main functions of the antenna mast: height adjustment, bore sight angle adjustment, and arm polarization adjustment. The height of the antenna is adjusted by pulling a pin from small holes on the stand. The pin should be placed into the corresponding pinhole to hold the arm in place once a desired height is reached. This was decided by the customer, who wanted a solution which would allow the height to be adjusted manually by the test technician, rather than the current mast in use at the lab, which is adjusted automatically using software. This helps reduce wear on the mast and requires the technician to be inside the chamber to ensure that the antenna is at the desired height before executing the measurements. The bore sight angle is adjusted by pulling a pin from slots which vary between +5 and -40 degrees. The pin should be placed into the respective pinhole to hold the arm in place once a desired angle is reached. This was decided by the customer, who also wanted a solution which would allow the bore sight angle to be adjusted manually by the test technician, rather than the current mast in use at the lab, which is adjusted automatically using software. Again, this requires the technician to be inside the chamber to ensure that the antenna is angled correctly before executing the measurements. The vertical and horizontal polarization positions of the antenna are able to be orientated by using a piston and cylinder assembly attached to a cam, which is attached to the mast arm. Once engaged, the pneumatic system pushes the piston up or down on the camshaft, which will move either closer or further from the axis of rotation to move the arm between horizontal and vertical polarizations. Software already in use at E3 compliance, a low-current microcontroller, and fiber optic cable are used to power the pneumatics controller. The microcontroller receives input from the test technician regarding whether the arm should be in the vertical or horizontal polarization, and this electronic signal with that information is converted to a light signal with the transmitter PCB. The signal then travels through a fiber optic cable to the receiver PCB inside the chamber, which actuates a pneumatic device that pushes air into the double-acting hydraulic cylinder from either the top or bottom, which pushes the piston down or up, respectively. This allows the arm to move either vertically or horizontally depending on what is desired by the technician. Thus, a completed antenna mast design that is able to be adjusted both manually and automatically by the test technician.